Hi everyone, welcome to Deep Learning Talks. So today we're going to talk about attention. Mostly we would like to answer why the hell do we need something like a multi-headed attention. So we have seen or observed in the previous videos where we talked about token embeddings, the whole language is represented as a lot of text, right? As if it's, all the text from the internet is scraped at one place. All of this text is now further represented as words. Text translates into words. Then words are further broken down into tokens. Now, how are these tokens represented? Each token is represented as an embedding. So we kind of imagine that what if Puru is a token and Puru is a token which is represented as a vector of 512 dimension. You can imagine Puru as a 512 dimension column vector. Now if Puru is a 512 dimension column vector, what what do we do with it? We have a lot of tokens in a language. Every token itself is an embedding. Every token in itself is a 512 dimension vector. Let's call it the dimension of the model or dk. Now, what do we want to do with it? We want ideally to make sense of the language. To be able to make sense of the language, we have a narrative that we follow, which is we want to produce contextual representation between all the tokens. Now, what is that? We want to quantify and come up with a score that can help us describe some sort of contextual representation between token 1 and token 2. Like hello, how. Let's say these are two tokens, Eiffel and tower. I want to be able to produce some contextual representation between token 1 and token 2. Now, the narrative goes like this. If I am able to produce the contextual representation between two tokens and I can do it over and over across all the tokens, across all the pairs of tokens, I might be able to build some sense of the language that is helpful in producing a representation in higher dimension that will further help me do the next token prediction. Right now, these 512 dimension token or this 512 dimension token embedding, let's not call them token. When you take a token and convert it into a 512 dimension token embedding or a vector, you simply call them embedding, and it need not be 512 dimension. Let's call them dk, right? Let's make it abstract. It need not be hard coded to 512 is a random name that came to my mind, and let's call it dk. Now, each of these token embedding, we know that we need to produce some contextual representation between token 1 and token 2, right? Let's imagine that we only have two tokens in our vocabulary, right? Now, what do we do? Every token has token embedding. Along with this, every token has three more things. The first thing that we will call as key, the second thing we'll call as query, the third thing we'll call as value. Now, what do I mean by that? Token 1 has a vector known as key. Token 1 has a vector known as query. Token 1 has a vector known as value. Now, imagine query, key, and value, or key, query, and value as three abstract ideas. So, the notion says that token 1 asks questions. So, when token 1 wants to ask question, we will think of it like query. Token 1 wants to query, out of all the token j, what is it that am I looking for? Now, token j, since it has been asked questions, it will have to offer some information. So what is it going to offer? The key component of token j will go like this: what do I have that other people are looking for? Now, similarly, the value notion for token j would basically say, if someone is looking at me, what information do I actually give them? So these are the three abstract ideas that helps us represent all the tokens: key, query, and value. Now, we can always correlate these ideas, with the database narrative. It's a very non-trivial, thinking about language and language kind of producing key, query, and value. But if we think about database, it gets a little easier. So, query is the concept that has always been, relevant in case of databases. Key also is a concept that is relevant in databases, and value also. So, query basically says, what am I looking for? Key basically says, what do I contain that other people might be querying for, that other people might be looking for? So value basically says, if someone is looking at me, what information do I actually give them? What is the value that I have? Now, why do we have these three vectors? Every game, everything is going on just to produce one thing: contextual representation. Contextual representation is a score. We want to make sense or quantify a score that can tell us the contextual representation between token 1 and token 2. Everything, every game or every idea is being widespread just to compute that score. Now, what happens is that key, query and value are going to be persistent for all the tokens. We want to quantify them. How do we quantify them? So the idea goes like this: token 1 and token 2, the key component of token 1 and the query component of token 2, we want to compute a similarity between them, right? Now this similarity is computed using a dot product. Okay, so before we move to the dot product, we have to know that these three ideas, key, query and value, they are nothing but matrices, right? So we have a key matrix, we have a query matrix, we have a value matrix, or rather vectors, right? So we have a key vector, value vector, query vector. Now all of these for every token, and we have it for every token, right? It's not like we only have it for a certain set of tokens that are in our vocabulary. For every token we will have token embedding, right, which describes the meaning of the token, right, or which is supposed to describe the meaning of the token. Positional embedding, which describes the relative position of the token with respect to other tokens. Key, query and value. So if we look at the formula for key, so key matrix is computed as input, which is x, into wk. Query is computed as input x into wq. Value is computed as input x into wv. So we have wq, wk and wv. These are the three weight matrices for each key, query and value respectively. Yes. So if they are weight matrices, that means we will somehow make them trainable, we will somehow make them learnable, and they are going to be part of our training algorithm, and they are going to get updated while the training happens, right? So okay, now that we know key, query and value, they are matrices, what is the size of the matrix? So to make all of them coherent, we have kept all of them as same size. So they follow the same size as the model or token embeddings. So let's say dk is the size of token embeddings, which is 512. Same is for key, and same is for query, and same is for value, right? Now what do we do? So we have to produce a score. Now the score has to go between token 1 and token 2. Now for token 1 I have token embedding, for token 1 I have position embedding, for token 1 I have key, for token 1 I have query, and I also have value. Similarly, for every token I have all of these things. Now the score that I have to produce between token 1 and token 2 says that why don't we take a dot product? Let's keep the embeddings aside. Let's keep the token embedding aside, positional embedding aside. Let's only talk about query, key and value. What if I take a dot product between the token 1's key and token 2's query, and that dot product is going to help me develop an opinion on similarity. If the vectors are more aligned, I will get a higher dot product. And if I can convert that dot product into a probability mass by using something like a softmax function, and then I can multiply the value vector with it and divide it by the model dimension to scale it down, right? Because the dot products can be arbitrarily large. Since there are 512 elements, when multiplied with another 512 elements and done a summation, we can get higher dot products. So what if we scale it down by dk or square root of dk? So this is how we come up with a score. So the score of attention works on this on the phenomena of producing a dot product between the key vector and the query vector, key vector of token I and query vector of token j, and then converting it into a probability mass using softmax, then multiplying it by value, and downscaling it or scaling it using the square root of dk. So this is the attention scores for all I comma j pairs, or for all nc2 pairs. So that means attention will help me produce a matrix of n square, right, which will carry the relationship or contextual representation between token 1 and token 2, token 1 and token 3, token 1 and token 4, and so on, right? So it's going to be a good order of n square matrix. That means attention carries at least order of n square complexity. Now the matrix that we have produced, we'll call it a single head of attention, right? Let's call it H1, right? So this self-attention or single-headed attention matrix helps us build an opinion on the contextual representation between all the tokens, right? Now the idea comes, we have this attention matrix. This attention matrix, we can correlate it with the idea of representation learning. We have produced a representation of a language in higher dimension, which will help us do maybe next token prediction. Now, where does multi-headed attention as a keyword comes into picture? So the idea of multi-headed attention says that, see, the language has more and more nuances, more and more relationships, right? Token 1 sometimes acts as a noun, sometimes acts as a subject, right? Token 2 can be a verb, so token 2 can be an adjective. So if we want to capture more and more relationship, deeper and hierarchical relationship. So in deep learning, we focus on these two words a lot, deeper and hierarchical. In CNNs, we put up more and more convolution blocks to capture deeper and hierarchical feature maps. In neural networks, we put up more and more hidden layers to capture deeper and hierarchical representation. In case of attention also, we put up multiple attention matrices. So order of n square matrix 1, which is, let's say, the head 1. Then we can produce one more matrix head 2, one more matrix head 3, one more matrix head 4, and see, no, all of these matrices are not going to be same, because if they're same, then they're completely redundant. We want them to capture unique, different relationships. Why do we want that? Because we know that there can be a relationship in a language, there can be a relationship between a subject and a noun. There can be a relationship between a noun and a verb. There can be a relationship between a subject and a verb, or a noun and an adjective. So we want the ability to be able to capture all of these relationships. So we use multiple such heads. One head, one matrix is known as self-attention, single head of attention. Computing multiple such attention scores to capture deeper and hierarchical relationship is known as multi-headed attention. That basically means that we are not forcing one single head of attention to give us all the perspectives of a language in one matrix. We are using multiple perspectives, multiple lenses to judge and build an opinion on the language. One head might learn long-term dependencies, long-range dependencies. Another head might learn only semantic similarity, right? So it's essentially going to help our transformer learn the relation between tokens, and then the relations of relations between, basically one level above. So token to relation, then relations of relation, right? That's how multi-headed attention is going to come into picture. Now, so now I have computed head 1, head 2, head 3, head 4, 4 heads. What do I do with it now before feeding it to a feed-forward neural network? Before feeding it to a feed-forward neural network, I will combine all of these heads. So I will concatenate all of these heads to build a holistic perspective and to combine all the information that we have gathered across multiple heads. So let's say each head was of sequence length or vocabulary length, comma, d of head. Now, once I combine sequence length, comma, d of head, let's say 4 times, because I had 4 such heads, I will get sequence length, comma, d of k, which is the token embedding, right? Which is the main model dimension, so called. So now that I have the concatenated information, I have mixed the information across all the heads. Now I combine or concatenate all of these heads and multiply it with another weight matrix. So this weight matrix is known as WO, or we also call them, or we also call it projection matrix. So WO is also a learnable projection matrix, right? So everything is combined into one concatenated representation, and then we multiply it with W. WO itself is learned. WO is going to belong to the same real, it's a set of real numbers of dimension D model cross D model, right? Because we are going to multiply it with sequence length, comma, D model, or DK. So WO also has to be, maintain the size of DK or D model cross D model or DK, right? We are using D model and DK interchangeably. So we are mixing the information across all the heads, right? So that all of these heads don't act as independent identical representation of a language. So we're kind of mixing all this information. So this is what really happens in case of multi-headed attention, and I hope this information was useful. I hope now you understand what is a single head and why do we need multiple heads, and what is the reason behind producing multiple heads of attention. Thank you.